Welcome back to another convolution session. This particular session I'm entitling Convolution, Intervals, and Limits. And what I'm hoping to drive home in this session is the fact that when you're computing these convolution integrals is you need to make sure that the intervals over which y of t is defined in terms of it may have a different functional form or its values in a particular interval, those interval limits are not the same as your integration limits that you use to evaluate or determine what the y of t expression actually is. I can't emphasize that enough. So you can't assume that the lower and upper limits of integration, those are not going to be the same as the interval in time in which the y of t function or waveform is defined. Let's look at an example. Here's a particular set of functions. X of t, you could view that as the input. H of t would be the impulse response, which is a very hypothetical scenario, but we're now wanting to find y of t, and this funny looking star symbol is how we abbreviate this convolution integral and say x of t convolved with h of t will give us our output y of t. In order to convolve these in the convolution integral, we need to flip and slide one of these waveforms. Actually, it would probably be easier to flip and slide h of t, since h of t begins at 0 and ends at 4, but I'm going to make it more difficult, but hopefully it will be more illuminating. I'm going to go ahead and flip and slide x of t, and that will make my limits on this flipped and slid x a little more complicated, but hopefully it will help us to see what's going on relative to these intervals and limits that I'm trying to drive home. In order to begin this process of determining the output y, we need to find x of t minus lambda. X of lambda, let me just draw pictures, is consistent with x of t, which I believe I had defined to have a magnitude of 4 over a time interval 2 to 5, and that's now lambda. X of minus lambda, if we now flip that around or across this lambda equals 0 or the vertical axis, that will now give us a non-zero waveform between the lambda values of minus 5 and minus 2, and we haven't adjusted the functional form of that x of lambda. It's still a constant value of 4. If we now want x of t minus lambda, where t is this adjustable parameter, now we introduce the t on both segments or endpoints in x of t. We still have, although it's maybe not drawn consistently, the amplitude hasn't changed. That's 4. The leftmost endpoint is t minus 5, and the rightmost endpoint is t minus 2. And in our convolution integral, we not only need x of t minus lambda, but we also need h of lambda. And h of lambda is consistent with h of t, which was this pulse waveform of amplitude 3 and duration 4, and there's h of lambda as a function of lambda. In order to find the output, we're going to find y of t by examining different, what I call overlap patterns, that exist when we start sliding x of t minus lambda through h of lambda. So we're going to find y of t by examining overlap patterns. And computing the integral as this parameter t moves from minus infinity from the far left to plus infinity or the far right. Let's look now, and what we're hopefully you're seeing is we're going to now superimpose these two waveforms, x of t minus lambda on top of h of lambda, and we're going to vary t in a way that allows us to start with a very negative value of t, which puts x of t minus lambda in the far left side of the sketch. We'll keep increasing t and slide it through h of lambda, and we'll try to compute the integral when we have different overlap patterns that exist in that sliding process. The very first overlap pattern, which is what I call an overlap, is really the case where we have no overlap. So the first overlap pattern is in fact when we have no overlap, and I hope this starts to become very clear. And what I like to do is I like to just sketch these. Here's my h of lambda. Here is my, and these are not drawn very accurately in terms of relative relationships of each other. Here, this one should have an amplitude of 4 and a width, if I remember right, of 3. And as long as this particular endpoint right there does not come up to this endpoint, these particular intervals where these are defined, or what I will call these support intervals, intervals of support, those do not overlap. And because of that, this particular pattern occurs when t minus 2 remains less than 0. Well, that actually we can clean up. We can just add 2 to both sides, and this pattern exists as long as t is less than 2, and the result of multiplying these point for point to obtain our y of t, you can see that since they do not, the magnitudes, the functional forms do not have any points in common or overlap in the support interval, our output is 0, and we now have at least the very first overlap pattern and expression for y of t. Y of t is 0 as long as t is less than 2. And that should be consistent with what we started out with in the beginning, which we were saying let's not apply our input until we actually have passed 2 units of time, even though our impulse response will start happening as soon as we hit it. We're not hitting it until time t equal 2, so we should not see an output until we apply the input. And with that in mind, we should expect the following result that we just had, which is y of t is equal to 0 as long as t is less than 2. That's sort of one way to check our answer. Let's now look at the next overlap pattern, or to tie this back to how I defined it, this session, this is another interval. If we look at this, what's going to happen? We're not moving or adjusting h of lambda. It's always going to just stay here and have a magnitude of 3 or functional form of 3 from 0 to lambda equal 4. What we're sliding through is this x of t minus lambda waveform, and it has limits of t minus 5 and t minus 2. What we want to do now is find when this pattern exists, this overlap pattern exists, and then actually compute the integral associated with this particular pattern. Let's just look at when this pattern is true. This pattern is true or exists when this particular endpoint in the x of t minus lambda has now slid beyond lambda equals 0. So this particular pattern is true as long as t minus 2 is greater than or equal to 0. We also see that this particular endpoint can't be crossing to the right of 4, and this endpoint can't be going through lambda equals 0. So we maybe don't see what's going to happen yet, so let's just write them all down and find out which of these conditions is going to happen sooner rather than later. We've said that t minus 2 needs to remain less than 4, or t minus 5 needs to be less than 0. Now let's just compute what these are. This just says that t is greater than or equal to 2, which says, okay, before we said as long as t was less than 2 we had 0. Now we're going to get some overlap going on. This, if we add 2 to both sides, says t is less than 6. If we add 5 to both sides, this says t is less than 5. So our first pattern is going to be true as long as t is greater than or equal to 2 and t is less than 5. Those are the most confining relationships for this particular pattern to exist. Let's now find so this pattern is true. Let me just go ahead and write that down. This pattern is true for t greater than or equal to 2 and less than 5. Now, what we want to do is figure out what's going to happen with the value or expression for y of t. We know what h of t equals, and we know what x of t minus lambda equals. What we need to do is put those inside the integrand of our integral, and our limits of integration are going to be where these intervals of support, which I've crosshatched in red and blue, when we have an overlap of red and blue crosshatches, that's going to actually be our interval of support, and that will define our limits of integration. So we found the interval over which this pattern is true. That's between 2 and 5. And now what we can say is y of t is going to be an integral. We have h of t, which had a magnitude of 3, and if that had an expression in terms of lambda or t's, we would have to plug that in. Right now it's a constant with respect to lambda. That's just 3. X of t minus lambda functionally is just equal to 4 d lambda. Again, if that was some function of time or lambda, you would need to put in that functional form. What we now need are these limits of integration, and we go back to our overlap pattern picture, and we see that the lower limit of integration is that left point, which is actually lambda equal to 0, and this point, which is t t minus 2. That's our upper limit of integration, and that's the interval where we have both the the red crosshatch and the blue crosshatch touching each other. So this particular integral is going to be evaluated from a lower limit of 0 and an upper limit of t minus 2. And what I want you to realize is that these limits, t minus 2 and 0, are not the same as the lower and upper values when this interval for y of t is true. We can now compute this integral. We have a constant, which will just be 12 lambda, and now we evaluate that at the upper and lower limits of integration. And we end up with 12 times the quantity t minus 2, or 12t minus 24. And now we need to go back and say, remember, those are when this expression, or this functional form for y of t, is going to be true when t is between or greater than 2 and less than 5. And that's now our second overlap pattern. We found that it was 0 for t less than 2. Now for t between 2 and 5, y of t has this functional form, which is really just a straight line that's going up with a slope of 12 and had a y-intercept of minus 24. Let's now look at the next overlap pattern. I hope you're starting to get the idea of this notion of overlap patterns, those intervals that are defined by the overlap, and the limits on the integration, and the fact that those intervals and limits, upper and lower values, are not necessarily equal. For the next overlap pattern, again, h hasn't changed, h of lambda. X of t minus lambda has changed, and remember the width of x of t minus lambda, that went from 2 to 5, so it has a width of 3, and that means then that the next pattern that we will see is when t minus 2 remains less than 4, and t minus 5 just starts to go through lambda equals 0. Or this particular pattern is true when t minus 5 is greater than or equal to 0 and t minus 2 is less than, whoops, I'm getting ahead of myself, is less than 4. Or if we solve these for t, we see t is greater than or equal to 5 and t is less than 6. That's the interval over which this y of t expression will be true. Now what we need to do is find our integral expression and evaluate that, and that's going to say that y of t is now this integral. H of t has a magnitude of 3, x of t minus lambda has a magnitude of 4, so our integrand functionally has not changed, which is true. And now our lower limit of integration, I hope that you see that that's this t minus 5. That's when these patterns, these crosshatch patterns, overlap, and we go up to t minus 2. And we now are in a position to perform this integration. The result is still 12 lambda. We now simply need to evaluate this at these new limits of integration, upper limit of t minus 2, lower limit of t minus 5. The t's cancel, so let's clean this up. inside here we have t minus t, and now we have minus 2 plus 5, or this simplifies to 3, and we then end up with 36, or a constant value. Y of t is now constant and equal to 36 over the interval when t exceeds 5 and remains less than 6. And again, 5 and 6 are not the same as t minus 5 and t minus 2. So our interval is not the same as our limit on our integral. The next overlap pattern is determined as we slide x of t minus lambda more to the right. H of lambda stays the same. Now, though, t minus 2 has crossed beyond 4. T minus 5 is still to the left of 4. And this pattern is going to be true when t minus 2 is greater than or equal to 4 and t minus 5 remains less than 4. Or this says t is greater than or equal to 6 and t is less than 9. When that's true, we have the following integral relationship. We have that pattern for x of t minus lambda and this pattern for h of lambda. Y of t is now h functionally is 3, x of t minus lambda is still 4. The lower limit of integration, I hope you can see, is t minus 5. The upper limit of integration is 4, and now we have 12 lambda evaluated from t minus 5 to 4. Or we now have, if we clean this up a little bit, we have minus t plus 9. Or we now have minus 12t plus 12 times 9, which is 90 plus 18, or 108. There's y of t, and that's going to be true for t greater than 6 and less than 9. And that's another functional form. This is the interval from 6 to 9, and this is the functional form for y of t. Now we have a negative sloping straight line, and if you check these different endpoints at t equals 6, if you plug that in as a check, that better equal what you just obtained for the previous overlap pattern. And I think the previous overlap pattern, when we were between 6 and 9, oh, I'm sorry, when we were between 5 and 6, we had a value of 36. If we now look at this expression, y at 6, we now have minus 12 times 6 plus 108. This is now minus 72 plus 108, or I think this looks to be 36, and that's a check, or that's consistent with what we had in the previous pattern of overlap. And that's a way that you can check your algebra. We now have our final overlap pattern, and like the one that we started with, this is actually when we have no overlap. Now t minus 5 is going to slide beyond h when it's non-zero. Here is our h of lambda. We now have x of t minus lambda, And this pattern is true when t minus 5 is greater than or equal to 4, or when t exceeds 9. And when t exceeds 9, I hope it's clear that these intervals of support are no longer intersecting or overlapping, and we then consequently have y of t equal to 0 for t greater than or equal to 9. And typically I would then summarize this and say y of t is equal to 0 for t less than 2. Now I'm going to have to go check my notes to remind me what we actually ended up with. Y of t was 12t minus 24 for t between 2 and 5. It was a constant 36 when t was between 5 and 6. It was then one of our more recent expressions, which was minus 12t plus 108, as long as t was between 6 and 9, and then it was 0 again when t was greater than 9. And that's maybe how I would summarize that output response due to the x of t and h of t that we started with. To finish this up, let me just make the following observation, that in the first time or two through this, people make this mistake, but the observation is that the overlap does not, and I can't emphasize that enough, the overlap does not mean that the functions h and x both have positive values. That's not what I mean by overlap. Overlap simply means that their intervals over which they're defined or supported, the overlap means their intervals of support overlap. For example, let me sort of draw a funny, as an example to illustrate that. Suppose that somebody gave you the following, and maybe they said, oh, here's your h of t. Maybe it starts at minus 1 and it is at 2. Here's then lambda. Then it goes negative, and maybe it's negative by a value of minus 4, and maybe it does that all the way up to 8, and maybe it transitions right at 3. Then maybe the x of t that they are convolving with this looks something like that, where this endpoint, let's say, is t, and maybe this endpoint is t minus 4. What I want you to realize is that the interval of support is going to be from t minus 4 all the way up to t. It doesn't matter that this particular x is negative and this h is positive, or vice versa. This portion of x is positive while this portion of h is negative. They still overlap. Their intervals of support overlap. And if you had to actually compute, if this x, let's just say functionally that we've determined that this x of t minus lambda was indeed, let's say, minus t plus lambda plus 2, let's say that's what it functionally was, then to compute this, I wouldn't worry so much about this point where x of t minus lambda transitions between 0 or negative and positive, because it still keeps the same functional form. What you might want to worry about is where h is changing functionally. It changes from a positive 2 to a minus 4, and I would then say that y of t, my expression to evaluate y of t under this overlap pattern, so that defines an interval of time when this is true, and this is going to be true as long as t minus 4 is less than 3 and t is greater than 3. That's when the overlap pattern exists. And y of t, I would actually break up into two integrals. I would say that the first integral, and the reason I would do that is to say that h of t is going to have a value of 2 from t minus 4 up to 3, and x is going to be minus t plus lambda plus 2. Again, we're integrating with respect to lambda, so t is just a variable or a fixed parameter in this integration process. And then we have another second integral defined from 3 up to t, and it will now be h, which is minus 4, times x, which is minus t plus lambda plus 2 d lambda. And we said that that was true. This functional form for y of t was true as long as t minus 4 was less than 3, and maybe you can't see it, so you say t is greater than 3 or t is less than 8. And that's because you have this particular portion of x of t minus lambda between 3 and 8. What you now do is you look at the intersection of these constraints, essentially. This now says t is less than t minus 4 we need to be less than 3 or bigger than 0. So now this says that t is going to be less than 7. What's another one? We also need to know, or can see, hopefully, that t minus 4 is bigger than 0. Again, you need to look at all of these possibilities. T minus 4 has now moved through or beyond lambda equals 0. So we now have all of these possibilities. We could have t greater than 4. We could have t minus 4 less than 3. We could have t greater than 3. Or we could have t less than 8. And now we take the smaller intersecting set of these constraints on our time. This now says that that one's active. If you look at this timeline, you now have 3 identified, you have 4 identified, you have 7 identified, and you have 8 identified. And what you're going to do is take this smallest interval, and so this integration functionally or functional form is true for the range t greater than or equal to 4 and less than 7. And that's when this particular convolution integral expression is valid, which I said is t between 4 and 7. I think that's enough for intervals and limits.